Alright, this third video on on vectors is going to be specifically on the unit vector. The unit vector. And this is a vector that has a magnitude of 1. So any vector that has a magnitude of 1 is called a unit vector. Now, believe it or not, we can take any vector and we can turn it in to the unit vector with the same direction. And the way we do that is with the reciprocal of the magnitude. So if vector v is a non-zero vector, if vector v is a non-zero vector, then vector u equals 1, or the unit vector here, where u is the unit vector, vector u equals 1 over the magnitude of vector v times vector v. This would give us the unit vector in the same direction as vector v. Okay, so for instance, let's look at an example. Let's find the unit vector u. So find the unit vector. Okay, with the same direction as vector v equals 3, 1. Well, how did we find that magnitude? Well, if you remember the formula, the magnitude, which is the absolute value of vector v, is equal to the square root of a squared plus b squared. A squared plus b squared. So this is going to be the square root of 3 squared plus 1 squared, which is the square root of 10. Okay? Now that's the magnitude. The magnitude. Let me write more slowly. That's the magnitude. And remember that it would be the absolute value of the square root of 10, but because this is positive, the absolute value bar is not necessary. So if we want to find the unit vector u, we multiply by 1 over the square root of 10. 1 over the square root of 10 is essentially going to be our scalar multiple. Okay? It's going to be our scalar that we're going to multiply by. So 1 over the magnitude, which we found, times vector v, which is 3, 1. So when you multiply that, you get 3 over the square root of 10 and 1 over the square root of 10. So this would be our unit vector u for our vector v, 3, 1. Now, if you want to check that, take 3 over the square root of 10 and 1 over the square root of 10, put it in our magnitude formula, and every unit vector should have a magnitude of 1. So plug it in, and you'll come out with a magnitude of 1. If you don't, then for that unit vector, then you know you've done something incorrectly. So there's always a way for you to check your work with that. Alright, so the unit vector u would be in the same direction as vector v. Now, we have two special unit vectors, okay, and they both occur on the axes. So if you look at the axis, this is the x and y, of course, we have a special unit vector that starts at the origin and goes up to here. Now remember, unit vectors are only length 1, so it has to go up to 1. We have a unit vector that goes up to length 1 there. That's called vector j. Vector j. We also have one on the x-axis that does the same thing. It goes up to where 1 is, and that is vector I. Now, they're very important because any vector v, okay, any vector v can be expressed as a linear combination of these two vectors, okay? Any vector v can be expressed as a linear combination, is what we call it. A linear combination of these two vectors. And the linear combination of these two vectors with vector AB would be A times vector I plus B times vector J. This would be the linear combination. So any vector v can be written as a linear combination of the vectors I and j. And these are unit vectors. So here's what I mean. If we have vector v, which is AB, and we want to write it as a linear combination of these two vectors, well, we're going to write it as, in terms of I, okay, in terms of I here, we would write it as A0, because notice I is on the x-axis where y is 0. And for vector j here, we would write 0b in terms of this linear combination of vectors I and j. So if you were to factor out A and factor out B, this would leave you with this right here. If I were to factor out an A of the first one and a B of the second one, that would give you this. Now, this is just a proof, okay? Don't overthink it a little bit. We're just factoring out. Now, look, 1, 0 is vector I here. So we would say that this is A times I. 0, 1 is vector j here. So that's B times j. So that's how we get that linear combination. Any vector AB can be written as that linear combination. A times vector I plus B times vector j. So, with these unit vectors, excuse me, with these unit vectors, our algebraic properties still work. What I want you to do is on page 388 in your book, page 388, at the very bottom of the page, you see the algebraic properties of vectors. Basically, these are like your addition and multiplication properties for real numbers. A lot of them are going to be very similar. You're probably not even going to have to memorize them. It's going to be so common sense to you by this point in your math life. So review over those. It's for instance, it's the commutative property, the associative property, the distributive property, things like those. But read over that table, and make sure that you know what's going on there, because that's going to help you with your properties and addition and multiplication on vectors. Okay. So, for instance, let's look at an example. All right. Express vector u, which is 2, -1, and v, which is 4, 5, as a linear combination, as linear combinations of the unit vectors I and j. I and j. Okay, so for instance, let's look at vector u plus vector v. vector u plus vector v. Well, first of all, we're writing these as linear combinations before we do the addition. Okay? So you've got to write vector u as a linear combination. Now remember, this is AB, AB, because remember, the linear combination is A times vector I plus V times vector J. Okay? So we have to write each of these individual vectors as this linear combination. So this is going to be 2 times vector I minus vector j, minus 1 times vector j. That should be a parenthesis. Both of those should be parentheses. Alright, plus, now convert vector u the same way. So this is going to be 4 times vector I plus 5 times vector j. Now you'll be able to combine your like terms and solve this problem. So you'll have 2i plus 4i gives me my 6i. And then negative 1j plus 5j gives me 4j. So 6i plus 4j would be the linear combination of those two vectors. Okay? 6i plus 4j. Alright, so let's look at another one. Let's do u minus v. So once again, no need to go about explaining this again because it's the same letters. The only difference here is with our sign in the middle, right? Now, think back to algebra. How did we deal with that? Well, we distributed it, right? So this is going to be 2 times vector I minus vector j minus a 4 vector I minus a 5 vector j. So we just basically did the distributive property just like you would do with addition and with basic algebra. Now combine your like terms. 2i minus 4i is a negative 2 times vector I, and negative j minus 5j should be a minus 6j. So the same way we would do that in algebra, we do it here. So distributive property does work here. Okay? Distributive property does work. Now the only thing I would caution you on is if you had something like this. Now we're going to convert this back, okay, to the linear combination before you multiply through by the scalar multiple. Then multiply through by the scalar multiple and you'll have your answer. But you have to convert it because we're using the unit vectors I and j, which remember, essentially what this says is unit vector I is this vector here, 0, 1. Oh, excuse me, 1, 0. The unit vector j is the vector 0, 1. So we're writing each of these, because these are on the axes, remember, we're writing each of these vectors as a combination of these two vectors. Okay, so keep that in mind as you're doing this. We just substitute I and j in instead of writing out 1, 0, and 0, 1 every time. Alright, so these are your unit vector properties. We have one more video, and I would do it with this video, but I want it to be a video all by itself. We have one application problem that I want to show you, and then we will be done with section 6.4.